Okay, so let's move to the topic of today's lecture. So what we would like to do is to minimize the function, minimize the objective function in the absence of constraints. So we have unconstrained optimization. And we are going to assume that we don't even have the gradient of the function available. Okay? And in such a case, we need to use gradient-free methods. And in today's lecture, we will cover two basic categories of gradient-free methods. The first one will be random search methods, represented by the Lucy-Yakola and the simulated annealing method. And then in the second part, we will cover essentially methods which only approximate the gradient based on some local measurements. And this would be the so-called extremum seeking algorithm and the Nelder-Mead method. So let us start with the first random search method, which is the Lucy-Yakola method. And Lucy-Yakola is a heuristic method for global optimization. Essentially, it is a method which, under certain conditions, can find the global optimum of a non-convex function. Which also means it is also applicable to convex functions, and it's actually even easier to implement when the objective function is convex, because then we know that all optima are global optima. Okay? But it also works for non-convex methods, non-convex functions, sorry. And it is a random method, and this is how it works. First, I will explain the idea graphically before moving to the code implementation. So it is a random method where we randomly pick up some initial point. So let's suppose that we would like to minimize this fancy function. The optimum is here around 1.15 or something like that. Let's suppose that initially we have picked up this point, say, minus 2.5. Okay? So we pick up the initial point, and we also pick up some interval around this initial choice. And then how this method works is that it generates random samples inside of this green interval. So we have the middle point and we have the interval. Inside of that green interval, we randomly pick up a new test point. And what we see here is that the value of this new point is better than the value of the previous point, okay? Because the function value is smaller. So what the method does, it says, this is a new point, which is better. Let's move the interval to this new point. So we essentially make this point the new center of our interval. And then we repeat. Meaning we again pick up some random point from the interval, and what we see here is that this new point now is worse than the previous one. So what this method now does, it shrinks this interval, because it says, oops, maybe I have gone too far. So it decreases this interval and does the same. Inside of the smaller interval, it again generates a new sample. And if the sample is better, it moves there. If it is worse, decreases the interval. Okay? So this is the kind of the general idea of this Lucy-Yakola method. And it works in arbitrary dimensions. So let's suppose we would like to minimize the very standard Goldstein price function, which has this nasty analytical expression. This is how the function looks like. It is non-convex function. However, it has a global minimum here at this point. So x is equal to 0 and y is minus 1 or something like that. And we would like to find this point. So what the Lucy-Yakola method does is illustrated again on the contour plot. So each of these lines here means that the function value is the same. So the global optimum is here. What we do is we pick up an initial point and we pick up some neighborhood of this initial point. And of course this neighborhood, I mean, it can be large, it can be small, depends on the parameters of the method. So we have the center point and we have the interval, and what we do is we start generating random samples. So we generate a random sample, and we take a look whether the function value here is better than at this point here. And here it is worse because we are trying to minimize, and in this direction the function value actually increases. Okay? So this point is worse than the original. So what we do is we shrink. Okay? So we take the box and we make it smaller. And we generate the next random sample. Okay? So it might be this one. This one is better. So what we do is we take the box and we simply translate it such that this point is the new center. Okay? And we repeat. Generate random points. This one is worse, so shrink. Okay? This one is better, so move. Okay? And we proceed with this until we eventually converge. So this is, in principle, what the Lucy-Yakola method is about. It is a random method because it generates random points. And then it is kind of a greedy method because when it sees improvement, it moves in that direction. Which also means that sometimes it can be stuck in a local optimum. Essentially, when the box is too small and we are around the local optimum, we will never escape that local solution. Okay? So that's, in principle, how it works. And now how it works in a more concrete terms. And what I also want to emphasize here is what do we require to know about the function to be minimized. So in gradient descent methods, we have seen that we do require the gradients and sometimes the Hessians. We didn't require the function itself. In these gradient-free methods, the tables are turned. So what we do require is just the measurement of the value function. We don't even need to know its analytical expression. Okay? We just need to know the value of the objective function for some point. So that's the required knowledge or the input to the method. And we need to know the boundaries of the initial search box. Okay? And then there is an initialization phase and there is iteration phase. So what we do in the initialization phase is that unless the starting point is given, we choose it as a random point from this interval. Okay? So if we have just one variable, then this is a line segment. If we have two variables, it is a box. If it is three, it's a cube, and so on and so forth. And this capital U here, that's the uniform random distribution. Essentially, we are generating a random number from BL to BU. Okay? And then we set D to be equal to the sampling range that's essentially the width of our box. Okay? So we have a box which is centered at X, and it has a width of 2D. Okay? So D is from the center to one side and from the center to the other side. Okay? So that's the initialization. And then come the iterations. So what we do is we pick up random vector, again as a random number from minus D to D. So essentially what this does, it picks a point relative to the center. Okay? Then we add this random vector to the center of the box to obtain a new sample. So this is just a fancy way of generating a point which is guaranteed in the box itself. Okay? So here we have generated a new box, and then comes a decision. If the new point is better, because we are minimizing, it has a smaller objective value, then we set the new center to be equal to this point. However, if the new point is worse, then we decrease the width of the box itself. Okay? And we keep iterating. Okay? However, here it's quite tricky to know when to terminate the iteration. So essentially, again, what we could do is when this D here is small enough, because we see that we are essentially always decreasing it. Okay? So when the D is already too small, say 10 to minus 6, then we abort the iterations. But we don't have any specific control about the convergence rate besides the value of D. Okay? And then this kind of formal description can be easily translated, for instance, to MATLAB. Okay? So we have a function, Lucy-Yakola, which takes the function to be minimized and the lower upper boundaries as the input. Here in this particular implementation, the function to be minimized is an anonymous function, so it's a function handle which provides the values of the objective function for some particular choices of x. And then we have the initialization phase where we generate the random starting point. We also get the width of the box in which we generate more samples, and we repeat until convergence. Okay. So at each iteration, what we do is actually here is a mistake. I'm sorry. Here it should be just no. Actually, this is fine. Yeah. It generates a random vector from -d to d. Okay, so this is rand here is a function which generates a random number between 0 and 1. Okay, so that's why we add -d and we have 2 times d here. Essentially, we are just translating the 0-1 interval to -dd. Okay, so it's just a linear transformation. Then we obtain the new point and we check convergence. This is also a way how to check convergence. Okay. We check whether the function values have already kind of converged, and if the new function value is better, then we set the new point to be the new center. Otherwise, we decrease the box. Okay, so very simple. Okay, so let us illustrate how the method works for the function that we have here.
Can I ask you?
Sure.
If you compare the runtime between this method and, for example, gradient method, which is worse?
Okay, so the gradient-based methods, depending on the choice of the initial point, can either converge here or it can converge to any of these local optima. However, these random methods are far less sensitive to the choice of the initial point. Essentially, okay, I will show the code in a second, but essentially, even though we have started originally here, where the gradient-based method would converge to this point, which is not the global point, this random method kind of escapes the local optimum because the original width of the box was like this. So essentially, it was covering the whole interval. So the next random point was here. And it has seen that, wow, we have found a point which is better than the point at the previous iteration. Okay? And sorry. Here, again, it was generating a random point. It might be that it has generated this point, which was worse. So it has decreases the range, generating a new point and eventually terminating here. So the general answer is those methods are not directly comparable because gradient descent methods are local, while these methods are global. Okay? How it would be for the convex function is a completely different topic. There, the gradient-based methods would be, I would expect them to be faster because they always go in the correct direction. While what the Lucy-Akola method would do for a convex function, it would start with this point and it would jump here, okay? Just to realize it's a worse solution. So it decreases, okay, let's say this is 2D, like the search of the width of the search space. Okay, so it would decrease this space here. Okay, but then again, it might generate a point which is worse. Okay, and we have already wasted 2 iterations. So again, it decreases, and it might find this point and it moves here. Okay, but then essentially it explores many possibilities which are worse, while the gradient descent methods, they always go in the direction of the improvement. Here, we also sometimes do not improve. We make the solution worse than it was before. Okay?
Is it possible that this Lucy-Akola method will end in local optimum?
It might, yeah. If the width of the box as chosen initially would be small, then like if it would be this big, it might be that we only essentially explore this little space around the local optimum. Yeah. So the original space has to be large in order, and even though we still don't have theoretical guarantees that it converges always to a global optimum. There are some conditions under which the method converges, and I will talk about them in a second. It does. Yeah, definitely. Okay, so and to illustrate that, let me show you how it works. Okay, so here Where is my mouse? Okay, so you see already 2 rounds of the method, okay? First one 250 iterations, the other one 260. And where is the plot? Here it is. Okay, so here it's 227. So what we see here is like we started here, and then it has moved around until this point. But yes, in general, these methods require quite a lot of iterations. And if I started the next time, then 267 iterations, well, partially because, and you see, before we have started here and we required less iterations, now we have started closer to the global optimum and we require more iterations. So these methods eventually do terminate, but it's unclear like what is the exact relation between the number of iterations and the properties of the function. Okay, sometimes it can be small number, sometimes it requires more iterations. Okay, but the advantage here is that we can also minimize non-convex functions. Okay, that's the message. So just a short summary of the method. So it is applicable to problems where we have very limited knowledge. Essentially, we don't require to know the gradients nor the Hessians. We only do require the objective function, but we don't even require the analytical form of that. Okay, we just need the measurements of the objective function. We don't need to know how the function looks like. And now to the convergence, it can be shown that for twice continuously differentiable functions, then this method terminates guaranteedly. However, the worst case termination is exponential in the number of variables. And this has something to do, if you imagine, in 1D we had a line segment and we were essentially generating random points in the line segment. In 2D, we are generating random samples in a box, okay? And we kind of, for good convergence, we do require that we cover the box, okay? In other words, let me put a different color. Also, this is a sampling of the box, okay? But it is not a particularly good sampling because we are essentially not exploring what happens above this line or below that line, okay? So for good performance of the function, we really do require that we cover the whole box with the random samples. And here is where the dimensionality comes into play, okay? So here we are in R2. Now imagine that we would like to grid a cube, okay? Just imagine that you want like kind of 10 points along each axis. And say it would not be a random sampling, but it would be a uniform sampling. What I mean by that is if this is 1D, then a uniform sampling would be like this. Okay, so the distance between each of these points is the same. A uniform sampling here would be, again, uniform distances. And here we have d squared of them, where these the required number of points. Here it's d to the power of 3. And for 10 variables, it's d to the power of 10 samples that we need to generate in each box to have good coverage. Okay? And this is what we call is an exponential growth of the complexity. Essentially, it means that this method would require an exponential number of points, meaning iterations, because each new point means one iteration of the algorithm. So this worst case scenario is exponential in the dimension because it requires to generate lots and lots of samples. Okay? And there is also a nice kind of a consequence of this complexity analysis, which was conducted by Yudin and Nemirovsky. What I basically say is there is no universal method to solve all problems. What we have seen before is we have gradient-based methods which are local but have kind of fast convergence. Here, these methods are global but have slow convergence. Essentially, there is always a problem somewhere. Okay? Either you find a local optimum quickly, or you attempt to find a global optimum after a long time. Okay? So there is no free lunch as we used to say. Okay?